Today we're going to build binary search trees in C. I'm going to start with a quick introduction to what a binary search tree is, and then we're going to write the code to create the tree in C. I'm going to leave searching the tree and deleting things from the tree to another day. Today is just about building the trees. A binary tree is a technique that we use to store information that has keys that can be sorted in a way that makes it easier to find things than a linked list would be. So the rule with a binary tree is that each node in the tree holds one thing, and all of the things that are smaller than something are in its left subtree, and all of the things that are bigger than something are in the right subtree. And we just keep a pointer to the root of the tree, and then we can find everything. So suppose that in this tree I was searching for 33. I would start at the root and I would say 33 is less than 42, so I should go into the left child of 42, and that gets me to the 21. And then I would say 33 is greater than 21, so that would make me go to the right child of 21, and there's my 33. And if I search for something that isn't there, we'll know that when we fall off the end of the tree. So for example, suppose that I'm searching for 60. Well, 60 is greater than 42, so I go to the right and get to the 56. 60 is greater than 56, so I try to go to the right, and there is no right subtree, so that tells me that there is no 60 in the tree. Now there are lots of really important things about the trees. They are recursive, every node is the root of a subtree, and the runtime analysis for search is a really important thing, but this video isn't about any of those things. This video is, if this is the structure that I want to build, how do I code it in C? Okay, so I have created an empty project. I've got the standard hello world main, and then I've created a C file and an H file to hold my stuff, but I haven't built anything yet. So I would normally start by building the struct that all of the rest of this is going to depend on, because that helps me think about what it is that I'm going to store. And so I'm going to start by making a struct binary. Well, no. I'm just going to call it a node struct. And each node is going to have an integer that is the key, or the value, we'll call it the key for that node. And then it's going to have a pointer to another one of these that is its left pointer, and a struct node struct that is its left pointer, and a struct node struct that is its right pointer. So I can store the key, and I can store the pointer to the left subtree, and I can store the pointer to the right subtree. And I have a type def around that because I don't like to say the word struct too often. So I'm just going to call this a node. And if I want a pointer to it, I'm going to call it a node pointer. Okay, so there's our node. When you have a node, the first thing you need to be able to do is you need to be able to create it. So I want a function that can return a node pointer. I'm going to create node, and I'm going to pass into it the key that you should store. Okay, so I need to write a test for that. It's easier for me to think if I write a test before I write the code. So if I used that, I'd have a node pointer, I'll call it the root for now, that is that I'm going to get from create node. And if I'm trying to make this tree, the first thing I want to do is put a 42 into it. I got to import my H file. Oh, create, that's a fascinating way to name that. Create node 42. And then if I did that, I should be able to check that the root, that node's key should be 42. And both of its children should be child pointers, its left and its right pointer, should be and I need to import assert there. So this should crash terribly. Undefined reference to create node. Well, that's because you didn't code anything for create node. So create node should look like this, but I need to put its implementation in the C file. And for now, I'm just going to return null. Why does it keep doing that? I have to like type it wrong and make it upset and then type it right. Oh, and make it still upset and then make it think it needs to import it, but it doesn't really need to import it. I can do that and then I can get rid of it later. I have no idea why my CLion is doing this, but it's not knowing what null is, even though it knew what null was over here. So I'm not sure why it knows what null is sometimes. I wonder if there's a null. Anyway, it doesn't matter. I have a null now. If I run this, it should crash because, and it does crash because create node is just returning null. And so when I do the root points to key, it's not going to be able to do that. So in create node, I should create a node pointer. I'm just going to call it node. And the first thing I have to do is callic it. And I'm going to use callic because that will null all of its child pointers, its left and its right pointers, because null is 0. I want one thing that is the size of a node. A node struct. And why does it not like that? That's why it doesn't like that. Import callic from malloc. All right, that looks fine. I think it's going to be complaining about, well, we'll use it, and then I think it's going to complain about the type. Node points to value, or to key, should be the key we gave it. And then I should return node. Again, because I did callic, it zeroed everything, so I don't have to null the 2 pointers. They got nulled by default. Yay, that test passed. And that's all I need for create a node. Whoops. So the next thing I'd like to do is to be able to put new nodes into the tree. So I'm going to say insert key, and I'm going to give it a node pointer that is the root of the tree I want to put that key into, and a value. So there it is. It's implementation, and because it's void, I don't need to do anything to make that okay. Then over here, after I've created my root, I'm going to try inserting something that should go to the left. So I'm going to say insert key from my root. I need something that is less than 42, so I'll do 21 because that's the thing that was to the left in our tree. And once that has happened, then I should check that I didn't screw up the root node. So essentially I want all of these for the root node, but now its left pointer should not be null because I should put my new node to the left of it. And then if I went root points to, root points to left, points to key should be 21, and that node, its left and right pointers should both be null. So that should fail right now because I haven't built anything. It did. It checked to see if the left pointer was not null, and it is null because I haven't built any code yet. So the easiest way to do this right now in insert key is to just put whatever key I got to the left, and that'll make my test pass. Because sometimes it's easier to think about, like, just do the trivial thing, and then as we add other options to where things should get inserted in the tree, we'll have to make the logic in insert key better. But for now, I can make that test pass by just creating a new node with the key that I was given in it, and then make the root left pointer point at new node. So at this point, if we were to think about this, well, none of these, oh, come on, don't fight with me. None of these exist yet, and none of these exist yet. All I'm trying to do is this part of the tree. So I'm adding 21 as the left pointer. The 42, the right pointer, is still null. So if I run my test, that finished with execute 0. So the only thing about this code is when I created all of this, there was a whole lot of copy and paste that I did. Essentially, there are 3 things that I want to check at every node. I want to check what its value is, and I want to check whether its left is null and whether its right is null. So I'm going to make a function that does those 3 asserts all at once. So I'm going to call it check one node. And the first parameter is going to be the pointer to the node we should check. And then there are 2 booleans. Left should be null, and right should be null, and what key it should have. So those are the 3 things that we want to check about it. I'm going to need to import bool. And then essentially I want to do these 3 asserts, but I'm passing in a node. I'm going to do something a little yucky, but kind of cool. Whether or not this is an equals or a not equals depends on this thing. So there's what's called a ternary operator in C that I can say, look at left should be null, and if it's true, then node points to left should be null. Otherwise, node points to left should not be null. So just as a short, if you haven't seen the ternary operator before, it's made up of 3 parts. The first one is a Boolean expression. If that's true, then it'll do the left, the second piece of code, the part between the question mark and the colon. And if the Boolean is false, it'll do the other one. So in this case, if I pass a true into left should be null, the assert will check if node left is null. If I pass a false into left should be null, then it'll use this piece of code and it'll check to make sure that node points to left is not null. And I want to do the same kind of thing for the right pointer, where every one of these should become right. Copy that. Okay, so with that function, all of these three asserts would get replaced by check one node. I'm looking at the root. Its left should be null, its right should be null, and its key should be 42. Oh, I didn't put the, oh, I did put the assert for the key. So all of those three things get replaced by that one thing. And then all of these three things get replaced by that. So after we have done the first insert where we put in the 21, at the root, the left should not be null because the 21 should be there. The right should be null, and the root's key should still be 42. And then if I go to root left pointer, both of its pointers should be null, and its key should be 21. Okay, so I have not changed what I'm testing here. I've just cleaned up the code to make it easier to see what's going on. But for good measure, I could do, ooh, assertion failed. Whoa. Oh, this should not be 42. This should be key. There we go. All cleaned up. So that would be, you know, the like red-green refactor that test-driven development says we should do. I did the red where I wrote the tests and then they failed because I hadn't yet built the stuff. And then I got to green. And then I did refactor, and that was to clean up my testing structure here because I didn't like that I was repeating these three asserts, these three kinds of assert, a lot of places. Okay, but we're clearly not done because we can't always just make every new thing that we add be the left subtree of the root. So let's test that we can add to the right. That's crappy spelling. So what I want to do is I want to now put this one in so that it would go there. Well, its pointer wouldn't go there. Stop that. Just those. Oh, fine. Just be silly like that. So I want to do this. So I'm going to insert 56, and then I'm going to check to make sure that the whole tree looks like this part. So now the tests become easier and easier to write. Oh, no, after your comment. There you go. So now I want to insert a 56. The root node should now have both of its children should not be null. The left node that has a 21 shouldn't be changed at all. And if I went to root points to right, both of its children should be null, but its value should be 56. Assertion failed. I got to red. And the thing that failed is on line 9, which is this line. It's checking when we do this test right here, the right now is null because I haven't built any code yet. So that's why it's failing there. Okay. So when I need to create the node, but then the choice of whether I make it to be the left node or the right node depends on whether the key is greater than the root value or less than the root value. So I want to say if the key is less than the root key, put it to the left. Otherwise, put it to the right. So when I come in here with the 21, because that value is less than the 42 in the root, we'll put it on the left-hand side. When I come in with the 56, because it is greater than the 42 in the root, we'll put it to the right side. Whoa, that worked. And let's just look around and make sure that we see in the debugger what we see in the tests. So I'm looking here, I have a pointer to the root. The root has a key of 42 and it has a left pointer and a right pointer. If I click on the left pointer, it has a key of 21 and no children. If I click on the right pointer, it has a key of 56 and no children. So right now this structure looks exactly like this tree up here. Now, if we were going to add anything else to this tree, we can't just stick it on the root. I mean, like up to this point, we've been kind of cheating by just sticking things on the root. Now we need to wander through the tree to figure out which node it becomes a child of, and then hook it into that node instead of always hooking it into the root. So essentially what we have to do is we start at the root, and whatever value we're trying to insert, we search for it in the tree. And when we get to that place where you fall off the tree looking for it, that's where we're going to add it. So for example, let's think about if we're going to add that 33. Start at the root. 33 is less than 42. So we go to the left. There is something there. So we go to the left and then we get to 21. And 33 is greater than 21, so we want to go to the right, but there is nothing to the right. We're going to find a null pointer there. That null pointer is what we want to change to be this. So I essentially have a sentinel controlled loop that is looking for null, and when that child is null, that's what will tell us that we need to place it there. We're going to let's do that 33. So now I want to insert a 33. The root node should be unchanged. The left node should now have its right pointer not be null. And if I did root left pointer's right pointer. So root's left pointer's right pointer. I'm looking at this node. It should have two null. Its left and right should be null, and its value should be 33. Its left and right should be null, and its value should be 33. So that's going to fail, and it does, but we know it should fail, so that's good that it fails. So now in here, I'm going to need a sentinel controlled loop that is searching for null. So I'm going to start out by having a pointer that's going to walk through the tree, and I'm going to start it at the root. Now, why is that unhappy? Oh, name it. Duh. So when I'm at the root, the place, whether I want to check its left pointer or its right pointer, depends on the value in the root and the value in the key. And that feels like a really complicated condition to me. So to write the code, I would say while the child in the direction that I want to go of. So I'm going to pass in where am I in the tree and what am I trying to insert. So for now, I'm just ignoring what's in that. I'm just saying, while the child that's in the direction that I want to go is not equal to null. So while there is something in the direction I want to go, then I want to go in that direction. So if the key is less than curs key, then I want her to be her to the left. Otherwise, whoa, cur should go cur points to right. Okay, so I think we need to talk about that a little bit more. Essentially, this sentinel controlled loop, I'm trying to walk through the tree, searching for the value that I'm trying to insert. So if it's less than the node that I'm at, I want to go to the node's left child. If it's greater than the node that I'm at, I want to go to the right child. But I don't want to do that if there's a null there, because if there's a null there, I'm at the right place to do the insertion. So I'm going to define. So the hard part of this is figuring out how to look for the null. And that's why I've pulled that out into a function. Okay, I just typed that return false because I needed to get rid of the red that is up there. Oh, not equal to null. I don't want, so it's giving me a warning down here. And I don't want to be checking for null. I want to be checking for true or false. So I don't need to compare it to anything. And now it's upset because it's always returning false. Fine. That's just because I needed to get rid of red. So now what I want to do is, if the key is less than what's in the node, I want to check to see if there's a null, there's a not null to the left. And if the key is, I want to check on the, if the key is greater than what's in the node, I want to check on the thing to the left. So I'm going to use another one of those ternary operators to do this. Well, maybe that's, if I was going to code it out for real, if the key is greater than node's key, then I want to return node points to right is not equal to null. Else I want to return node points to left. And we're going to need to talk about this again because that was a big jump there. Sorry. So I'm comparing the key to the node's key to decide whether I care about the right child or the left child. So if the key is bigger than node's key, I care about the right child. If it's less than it, I care about the left child. And then the way I worded the name of this function is child in direction of. So it should be true if there is a child that way, which means it should be true if that pointer is not null. So that's why I checked if each pointer is not equal to null. I could have coded this with a ternary operator like I used in the other place, but to be honest, I think this looks a little better this way. I was going to turn it into a ternary operator after I built it, but I kind of like it like this. So let's just leave it like this. So I think what I have coded here is while there's not a null in the direction we want to go, we go the direction we want to go. And so this loop will stop when it's sitting on a node that has a null in the direction we want to go. So in this case, where I'm adding this 33, before I add this 33, we're sitting at this. We're going to first see, is the left child null? And it's not, so we're going to go that way. And then we're going to look to see, is the right child null? And it is. So we're going to stop at this node right here. When we do, now we're at the place that we want it to be. If the key is less than, then we're going to put it at the left side. Otherwise, we're going to put it at the right side. So notice, like, this was the same thing that we did when we were just playing with the root. The only difference is we've had to wander down the tree to find the right node to put it on instead of just always putting it on the root node. Let's see if this works. Ah, it did. Magical. Let's watch it work because it'll make me feel better if we watch it work. So I'm going to run it in the debugger. And again, I'm sitting here and I have my root has a 42, its left child has a 21 and no more children. Its right child has a 56 and no more children. So that's where I am at this moment. If I step into insert key, I'm going to create my new node. And then cur is going to start at the root. I'm going to close these up so we can see. Cur starts at the root, and we know that because it has a 42 in it. The new node that we've created has the 33 in it, so that's the one we're ready to hook into the tree. So if we step into this child in direction of, it's going to compare 33 to the 42 that we're looking at, and because it's less than, it's going to check the left child for null. And because the left child is not equal to null, that's going to return true. So this returns true. We go into the loop, and then we update cur to point at the thing in that direction. So now cur is pointing at the 21. When we step into child in the direction of, the 33 is bigger than the 21, so it's going to look at the right pointer. The right pointer is null, so this is going to return false. There is not a child in the direction that we want to go. That's going to make our loop stop. And so now we're sitting with cur at the node 21, which is the one we want to hook it into. And it's going to make it be the right pointer because the key is bigger. The key is bigger than current key. Yeah. And so it's going to make it be the right pointer. That's going to put this right there, just like we want it to. So the tests pass because we built it correctly. And as one last test of thoroughness, let's add this one in. Well, let's do them both. So let's start by, let's do this. So we want to put the 48 in. And so if I did that, go right, then left. So that would be put in the 48. The root should be unchanged. The left node should be unchanged. The right node should now have a left that is not null. So this should be false. And then if we do check one node, root points to right, points to left, root points to right, points to left, should have a value of 48. And I think we have coded this so it will pass instantly. And it does. And if we did, just to make sure that we can get things that go all in the same direction, we could do this 16 as well, and it should end up over here. So if I took all of this and, whoa, a line at least, add 16 now, the root is unchanged. The root's left pointer should now, neither one of the things should be null, so this should become false. And then we should have one more node that's going to have a 16, and it's going to be root points to left, points to left. Root points to left, points to left should have 2 null children and a key of 16. Yes, and just for giggles, let's look at our tree. The root has 2 children. Its left child is 21, and it has no... Oh, I stopped at the wrong breakpoint. That was a little panic. Thank you very much. Let's go on. Okay. Now, the root has a key of 42. It has a left that has a key of 42 or 21. It should have left is 13 and right is left is 16 and right is 33. Yep. Okay, so all of those are right. And then if we look at the right pointer of the root, it should have a 56. Its left should have a 48, and its right should be null. So we've built the tree that we wanted to build. If you enjoyed that, please like and subscribe so other people can find it. And click on another video because I build some other fun stuff too.